Very good afternoon. The, the objective of this session is to give an introduction about power quality. Basically, we have to define the power quality, and the power quality is defined as either voltage quality or current quality. It is aimed at maintaining the system's voltage or current as a pure sinusoid with 1 per unit as a magnitude and the frequency of 1 per unit. And in case of a three-phase system voltages, then the phase shifts between the voltages of the adjacent phases should be 120 degrees to each other. And the ultimate aim of maintaining the power quality is to reduce the losses and to improve by maintaining the power factor to be unity always in the system. So this is the system of three-phase voltages in which all the three-phase voltages are balanced sinusoid. So balance in the sense, if you consider all the phases are having the same voltage, same frequency, and the phase displacement between the voltages of the adjacent phase is 120 degree, and this is the time domain representation of voltages and the corresponding phasor diagram. So we consider three phases A, B and C, and if you observe, all the phasors are of equal magnitude, equal length, and the angle between the phasors are 120 degree, and all these three set of vectors rotates at a constant speed of omega radians per second, which means the frequency of all the three phase voltages are same. The characterization of electric power quality. So basically here, what are the disturbances we feel? Any deviation, and generally any deviation in the magnitude, frequency or the phase are considered as the disturbances which are factors which are affecting the power quality of a distribution system. So these elements are categorized as transients, short duration and long duration voltage variation, voltage imbalance, waveform distortion, voltage fluctuation and power frequency variation. Let's discuss about each and every parameters individually. So transients, and this is a kind of short duration phenomena. The causes are a sudden load throw, a sudden switching on of large loads due to the external disturbances which cause the shift of operating point of the system. So transients present in the system for a very short duration up to the few cycles of the input voltage. So this will lead to the increase and decrease in the magnitude of voltages, and the transients are categorized into two types, namely impulsive transients and oscillatory transients. So impulsive transients arises in the system due to lightning or any other faults. The oscillatory transients may be due to switching on and switching off operation. So these are the examples of some transient waveforms which occurs due to switching of voltage loads in the system. The figure 1, it shows that switching transients. So these are going to be the impulsive in nature, these transients, and if you observe this part, it seems to be oscillating. It means that it is keep on varying, the magnitude is keep on varying. And on the other side, you can see the image, the transients which arises due to switching in a power converter, in a PWM converter. The next category is short duration and long duration voltage variation. So here the voltages are subjected to a voltage variation, that's variation only in the magnitude, and we assume the frequency and the phase angle between the voltages remains constant and it's at the specified values, but the voltage magnitude may fall or may rise from 1 per unit magnitude. And these magnitude variations are characterized based on time. That is, if the voltage variation lasts for the period of less than 1 minute, then Such magnitude variations are categorized under short duration variation, and it is further classified as sag, swell, and voltage fluctuations. Similarly, the similar kind of magnitude variation is observed for more than 1 minute, then such a kind of problems are categorized as long duration variation, and it is classified as under voltage, over voltage, and voltage fluctuations. So let's see about the definitions for sag, swell, interruption. So whatever is the voltage rating of the system, it is better to refer in its equivalent per unit representation so that the definitions are applicable throughout the system. So that's why here the definitions will be purely meant based on the per unit values. Sag is nothing but the reduction in the RMS voltage between 0.1 per unit to 0.9 per unit for the duration less than 1 minute. And swell, it is defined as the increase in RMS voltage between 1.1 to 1.9 per unit for the duration less than 1 minute. Then interruption, that is if the RMS voltage falls below 0.1 per unit, it is for the duration less than 1 minute, it is called momentary interruption. So practically we refer this condition as a brownout condition or a blackout condition. In a conventional way we refer it as power cut. Under voltage, over voltage, and interruptions. So these parameters falls under long duration voltage variation. So an under voltage is characterized by the reduction in RMS voltage between 1.1 to 0.9 per unit for the duration more than a minute, and similarly over voltage is characterized as increase in RMS voltage between 1.1 to 1.9 per unit for the duration more than a minute. And the interruption, here the RMS voltage falls below 0.1 per unit for the duration more than a minute, and it is called sustained interruption. So there is no other significant term for the interruption which is categorized under short duration and the long duration. But here in general we'll refer for the short duration it's called momentary interruption, and for the long duration it's called sustained interruption. The next parameter is voltage imbalance. The voltage imbalance is the phenomena which occurs in a three-phase system where the phases are not balanced. So here there may be the variation in the voltage magnitude, or there may be the variation in the phase angle between the voltages, or both the variation in the voltage magnitude and the phase angle. Normally there won't be any imbalance in frequency because from a generator which is rotating at a constant speed, the frequency of the induced EMF in all the three phases remains constant. So the frequency parameter will not come into picture in this case. So the impact of this voltage imbalance is it will circulate unbalanced current when the load is balanced, and this results in neutral current and or its increased magnitude, which means I can say it's a neutral overloading. And any imbalance in phase or magnitude or both results in unbalanced currents and neutral overloading in the system. So these are the diagrams which predicts the unbalance in a system under different condition. So previously we have seen the voltages and phases of the system under balanced condition. So here you can see the time domain waveforms. Here if I observe the phase angle between the adjacent system voltages, are between these two phases it's 120 degree, and between these two phases it's not equal to 120 degrees. And similarly if you consider the magnitude, here it is at some magnitude, here the peak value is at some value, and for this particular phase the peak value is at some different value, which means that this waveform, this critical waveform contains both voltage unbalance and phase angle imbalance. So here I can say I can consider in terms of phasor. So here for the first case, if you observe, the magnitudes of the voltages are not equal, But if you observe the system voltages, the phase angle between the systems, it remains same, which means that there is absence of phase imbalance but only magnitude imbalance is present. The next case, I can say all the three phase voltages are having different magnitudes, and if you observe the angle between the adjacent phase voltages are, are not equal. So which means that this is a phasor system. This is a system which has both voltage, magnitude and phase imbalance present in the case. In some cases, there may be the magnitude of the three phase voltages may be same, but the phase angle between the adjacent phase voltages may be different and it's not equal to 120 degree. Practically this is not a this is not possible. The reason is the phase shift between the voltages is dependent mostly on the winding configuration of the alternator. Furthermore, if there is a phase imbalance, that may be due to the line reactance, unbalanced line reactance, or maybe the unbalanced line impedance of the load and the transformer. The next category is a waveform distortion. So basically we'll define either the voltage or current of the system as a sinusoidal function of time. If any deviation in the current or voltage waveform from the ideal sinusoid are considered as the waveform distortion. So this non-sinusoidal voltage or current will increase the system losses and the heating of the loads, and further it may cause voltage fluctuations and flickering. A typical example of a nonlinear load to which the applied voltage is sinusoid but the current drawn by the load is totally distorted in this case, and this is in a three-phase rectifier. The system voltage is sinusoid but the current drawn by the rectifier in one particular phase is not a sinusoid. It is exhibiting a different characteristic waveform. So which means that the system voltage is sinusoid but the current is not sinusoid. The waveform distortion can be characterized under different categories, namely DC offset, harmonics, spikes, notches and noise. And in harmonics we have two subcategories as interharmonics and the subharmonics. So first we'll consider about the DC offset. So DC offset is nothing but the presence of DC component in an AC system. So this may be arise due to the presence of a rectifier which introduces more DC component into the system. Harmonics, the definition of harmonics holds good and it is also a sinusoid voltage or current signal but whose frequency is the integer multiples of the fundamental frequency. And again we have two subcategories of the harmonics. One is interharmonics and another one is subharmonics. So in the interharmonics, the frequency of these sinusoids are non-integer multiples of the fundamental frequency, and the subharmonics, the sinusoid frequencies which are fractional multiples of the fundamental frequency. For an example, I can categorize a harmonics voltage as an integer multiples. Let us say that the system frequency is 50 Hertz and I am having a signal of 100 Hertz, 150 Hertz, 200 Hertz, 250 Hertz, 300 Hertz, 350 Hertz and so on. If I divide all these with the fundamental frequency, then I'll get 50 Hertz as n equal to 1, that is harmonic 1 or the fundamental component, and 100 Hertz n equal to 2, second harmonic, and similarly 150 corresponds to third harmonic, 200 fourth harmonic, 250 as a fifth harmonic. In our system, for a sinusoid voltage, we don't have even harmonic components. That is, we have harmonics on the order of 1, 3, 5, 7, 9, 11 and so on in a single phase system. And in case of three phase system, we have 5, 7, 11, 13, 17, 19, 23, 20, 23, 27 and so on. And interharmonics, I can say integer, non-integer multiples of the fundamental frequency. That is, if let us say in my system I am having a frequency of 75 Hz, which corresponds to 1.25 times of the fundamental frequency. So this fractional or the non-integer multiples will come under interharmonics and subharmonics. So these are the frequency signals whose frequency is less than 50 Hz and less than the system's base frequency are called subharmonics. Spikes are nothing but the sudden increase in the magnitude of voltage, and not just sudden dip in the voltage magnitude. Noise is uncharacterized signal. So coming to the voltage fluctuation, it is the characteristics in which only the voltage magnitude of the system voltage is not equal to 1 per unit in any of the phases or all the phases of the system. Here again there is a difference between the voltage fluctuation and the voltage sag or swell or over voltage or under voltage. So here in the system we allow the tolerance of about 10%, which means that the voltage under normal operating condition may fluctuate between 0.9 per unit to 1.1 per unit. If the voltage magnitude varies between 0.9 to 1.1 per unit, then the corresponding character is called the voltage fluctuation. So what is the resultant of this? So this may result in unbalanced voltages, that is fluctuating voltages and fluctuating currents. And sometimes this, if it is in a three-phase system, this will result in unbalanced current and neutral overloading and overheating of the load equipments. And the causes may be due to the varying loads, unsymmetrical faults or other climatic conditions. Power frequency variation. So here the characterization is based on the frequency. If the frequency of the system is not 1 per unit, then it is termed as the power frequency variation. And this may be the problem due to the sudden load variations on the system. A sudden load throw will cause the system frequency to increase beyond 1 per unit, and similarly a sudden loading will cause the system frequency to dip below 1 per unit. So so the basic reason is when there is a sudden load throw in a system, which means that the torque supplied by the generator prime movers will be more, and because of that the generator will get speed up and hence the frequency of the system will increase. Or if if there is a large load is switched into the system, this will cause a sudden dip in the voltage due to armature reaction, and this will slow down the alternator and hence the turbine, and hence this will result in frequency less than 1 per unit. So the variation in frequency will result only due to the speed changes or any malfunction of the load equipment, and such as triggering of the thyristor converters. So the next thing is about the power acceptability curves. So whatever is the conditions we studied so far are the basic characteristics of the power quality parameters, and we have certain system, or we have certain norms which allows or which dictates this is the variation in the system voltage limits as a function of time. So if that is the case, we have two curves which is going to govern the variation, which is going to express the variation in the voltage magnitude as a function of time. And these two curves are derived based on the functioning of a IBM computer in a bar system. That is, we are considering a sensitive load. So we know that computers are sensitive to load. If the voltage fluctuation is high, this may lead to the restarting of the computer, and if this persists over a period of time, this may lead to malfunctioning or failure of the motherboards or the processor. So that's why basically these standards are derived based on the working of the computer. So CBA, we have two curves, CBMA curve and ITA curve. So the CBA-MA curve is proposed by Computer Business Equipment Manufacturer Association. So where they are given the variation in the voltage as a function of time, both under over voltage condition and under voltage condition, and along with the as a function of time. So this is a continuous curve which we are going to discuss here, and this is a modification was given by the for this curve, and it is called ITA curve, that is Information Technology Industry Council curve, which it shows the discrete variation in the voltage magnitude as a function of the number of cycles of your supply voltage. So 0.001 C in the sense 1 by 100% of the cycle time period. So this diagram shows the number of cycles per second, and that is the voltage variation as a percentage as a function of the number of cycles of your supply voltage and its corresponding impacts. So this region corresponds to, that is where the voltage magnitude corresponds to more than 300% are considered as a short duration impulses, and are most frequently measured as the maximum voltage deviation from the power frequency sine wave, or as peak to peak volts measured through a high pass filter of a coupling capacitor. And this a system, which means that a system can withstand a voltage of about 300% for the duration of 0.01 cycles, that is which corresponds to 100 microseconds on a time scale. And similarly, a system can withstand 200% of the over voltage of the applied voltage for the duration of less than 0.1 cycle on time scale, which is corresponds to the duration less than 1 millisecond. So if I consider the 0.1 second or 0.5 seconds, the system voltage must be less than 110%, which is about the allowable tolerance of 10%, no? Plus 10%. And similarly, a system can perform well without any deviation or malfunctioning under voltage condition for this specified duration, which is represented by this CBMA curve. So what are the general problems associated with the power quality? The first thing is poor load power factor, the nonlinear and unbalanced loads, the power quality indices, modeling of harmonic distortion. So here in the modeling harmonic distortion, we have two categories. One is on total harmonic distortion, the other one is total demand distortion. There is a slight difference between total harmonic distortion and the total demand distortion. First, we have to define what a nonlinear load is, and based on this we have to provide the classification. So loads are classified into two broad categories based on the terminal voltage and current relationship, as the linear loads and the nonlinear loads. The linear loads are defined as the loads in which the voltage and current are sinusoidal and may be phase or out of phase with each other. Ideally speaking, the current, both voltage and current, must be in phase and the power factor of the system must be unity. This is going to be the definition of a linear load under ideal condition. And non-linear load on the other side, in which the system voltage and current are not in phase and the waveforms may be sinusoidal or non-sinusoidal. So all electronic loads or all the practical loads will fall under this category. Then the indices or the factors to be measured to quantify the power quality problems. The first factor comes here is total harmonic distortion, the power factor, telephone influence factor, C message index, IT product, VT product, K factor, crest factor, unbalance factor, and flicker factor. So let us see what is the main application of these indices on the system performance. The total harmonic distortion, and it is used for general purpose standards, and it is a very commonly used indices to measure the impact produced by a nonlinear load on the system. So as per the guidelines, the THD of current or voltage in any system must be less than 5%, and power factor, and this is potentially used in the revenue metering. Telephone influence factor, and this is the measure which is going to give the audio circuit interference, that is the interference due to the harmonics present in the voltage or current waveform with the neighboring communication lines. And C message index is used for communication interference. IT product, it is used for audio circuit interference and for measuring the shunt capacitor stress. VT product is used for quantifying the voltage distortion index. K factor, it is about the transformer derating. Crest factor is used for measuring or quantifying the dielectric stress. Unbalance factor, to measure the degree of unbalance in a three-phase circuit. Flicker factor, so this is based on the incandescent lamp operation and the bus voltage regulation and sufficiency of short circuit capacity. So let us discuss about a few factors. The total harmonic distortion. So basically it is defined as the measure of closeness of a waveform with respect to its fundamental component, and it's an important measurement parameter on the performance of an electrical system. So mathematically this is expressed as summation I equal to 2 to infinity I square divided by I1 square, where I is the magnitude of RMS magnitude of the ith harmonic component, and I1 is the magnitude of the fundamental RMS magnitude of the fundamental component. And this definition holds good for both voltage and current. And in order to evaluate the total harmonic distortion, the Fourier series is the mathematical tool to extract the fundamental and the harmonic components from a distorted waveform. And telephone influence factor, and this is used to estimate the effect of power line harmonics on nearby analog telephone conductors. And in this method, the magnitude of each harmonics is weighted based on the physiological and audiological characteristics of human hearing. So the reason here is the conductor which is carrying electricity and the conductor which is carrying a signal will have a different characteristics, impedance and different characteristics. So that's why we are measuring the telephone influence factor for different harmonics with different weights. So that's why mathematically, if you want to express the impact of the power line harmonics on the nearby telephone conductors, telephone lines, then I have to use with weighted values for the individual harmonics. So that's why I'll be having the expression as summation I equal to 1 to infinity wi xi the whole square divided by square root of summation I equal to 1 to infinity xi the whole square, where xi is a single frequency voltage or current of harmonic frequency I, and wi is the single frequency TIF weighting factor at harmonic high. Total demand distortion, and it's a measure of THD taking into account the circuit rating. That is, this is total demand distortion is similar to that of THD. The one difference between the THD and total demand distortion is, in the total demand distortion, considers the maximum short circuit capacity available at the point of evaluation. So as the circuit rating varies, the load current increases and hence the TDD drops. So the mathematical relation between TSD and TDD is expressed as TDD equal to THD multiplied by the fundamental current upon the circuit rating. The circuit rating is nothing but the maximum current which can be delivered by the system at the rated voltage and the rated frequency. Next factor is the crest factor, and it is used to describe the amount of distortion present in a waveform, and mathematically it is represented as the ratio of peak value to the RMS value of waveform, and it is used to express the dynamic range of measurement device. K factor, and this is a vital factor and it is very important power quality index, so which takes into account the additional heating of the power transformer that results from the presence of harmonics in the system. Which means that if a transformer is rated for 10 kVA and it is supplying a load of 8 kVA, and let us assume the load draws the fundamental power of 8 kVA plus the transformer is supplying 1 kVA of harmonic power. So if that is the case, in general, if I use a 8 kVA transformer for delivering a 8 kVA load, if the load contains harmonics and it draws excess power from the system, so this excess power or the harmonic frequencies, the harmonic currents and voltages will increase the losses in the system, and hence the power output of the transformer will be less than 8 kVA. So in order to meet such requirement, I should go for a specially designed transformers called K-rated transformer, so which includes the additional heating effect due to the presence of the harmonic current and the voltage. So the K factor is measured as summation n equal to 1 to infinity hn square into n square divided by summation n equal to 1 to infinity upon hn square, where hn is the magnitude of the nth harmonic. So the K factor is required must in a system for providing oversizing of the transformer. Next is the recommended practices and requirements for harmonic control in electric power system, and actually this is the guideline provided by the IEEE, the International Society of Electrical and Electronics Engineer, under the clause of 519. So IEEE 519 is nothing but it's a, you can say in general it's a harmonic standard, but basically it is a recommendation provided by the engineers to study or to evaluate the power quality. So in order to understand the guidelines, first we have to know the point of common coupling. So the point of common coupling is a point of metering or any point as long as both utility and customer can either access the point for direct measurements of harmonic indices meaningful to both, or estimate the harmonic indices at the point of interference through mutually agreeable methods. So I can define the point of common coupling in a system as it's going to, I can say it's a common meeting point, like as an analogous, so where either utility or the customer can access the measurements, can do measurements. So normally that is nothing but a metering point. Even at our home, the point of common coupling will be the metering board, because the person from electricity board will come and access our voltage only at the metering point, and even you can access a metering point. You won't allow the person to enter beyond the metering point for the measurement. So this is somewhat similar. the point of common coupling, the definition is somewhat similar, but the range is going to be in a different way, and the measurement is going to be a somewhat detailed measurement. So in our torque form we will perform only the power measurement, but here it's quite different. That is, apart from power we will be measuring the nature of voltage and the nature of current. And within an industrial load, the point of common coupling is the point between the nonlinear and other loads. So here we'll be using two terms. ISC is the maximum short circuit current at PCC, and IL is the maximum demand load current at PCC. So this is calculated as an average current of maximum demands over a period of 12 preceding months. So why this is required? Why the maximum demand load current is required? So before commissioning a load, before commissioning an industry, a system should have a knowledge about what will be the maximum demand required by the industry during its operation, and what is the level that a utility can provide for its customer. So coming to detail with IEEE 519. So it's a US standard for maintaining harmonic limits in the power system, and it's a simply guideline to follow the recommended practice for maintaining the harmonic levels, and we are accepting that as a standard. So the underlying philosophy is that the customer should not limit harmonic currents. The customer should limit the harmonic currents, the utility should limit the harmonic voltages, and both parties have the responsibility in holding the harmonic levels in check. Which means that as a utility, I should provide a voltage which is harmonic free, and you are the customer, you should draw the current from the system which is sinusoid, or if the current is non-sinusoid, then you have to meet the harmonic current limits. You have to satisfy the harmonic current limits. So in such a case, in order to maintain a better power quality, both the parties, that is the both utility and the customer, they are sharing the responsibility in maintaining the system harmonic levels. And so it's a guideline and not a standard or legal document, and it just provides a framework for the engineers to design the system, and it is applicable to all voltage levels, including the limits and the prohibition of the DC voltages, and it has been adopted by many utilities and public utility commission. So the utility should maintain the voltage THD limits under two category of voltage levels. One is below 69 kV and above 69 kV. So for voltages below 69 kV and below, the individual voltage harmonic distortion should be limited to 3%, and the THD in the voltage must be limited to 5%. And similarly, for the utility should maintain the current THD within the limits under two category of voltages, that is again above 69 kV and below 69 kV. So for PCC voltages of 69 kV and below, where maximum customers fall under this category, for different harmonic levels and for different ratios of the short circuit current to the maximum load demand, the THD values and the TDD values are listed in this table. So even odd order harmonics are limited to 25% of the average value listed against the odd harmonics listed above. But practically, if you consider, even harmonics are 0 in the ideal condition, but due to the increase in the power electronic load equipments, in some cases which introduces unsymmetric currents and voltages, so there may be presence of even order harmonics in the system, and hence the magnitude of such even harmonics must be limited to 25% of the corresponding value against the odd order harmonics. For an example, for the current ISC by IL ratio for less than 20, if the TDD is 5% for odd harmonics, then it should be 25% of this, which means that the TDD for even harmonics is limited to 1.25. and the loads producing DC offset or component are strictly prohibited in the system. Next is about IEEE 519. That is, this is going to as I told you earlier, this is a guideline. So how to interact with the customers for the measurement or for analyzing the power quality. So first of all, what are the things required? First is the modeling of the system from the customer side. The data required are one-line drawings of the customer's facility showing the ratings and connections of all the electrical equipment, location, connection, size and control method of capacitors, conductor sizes and impedances, location and type of nonlinear loads, overall plant load and the portion that is nonlinear, and location, rating, connection and impedance of transformers. From the utility side, the data required are available fault duty at the customer's location, ultimate available fault current, impedance and ratings of the service transformer, and possible voltage range variation. And the utility may need copies of customer's harmonic analysis for review prior to the approving the customer's proposed facilities. And the utility may need the customer to submit the manufacturer's documentation and test the data demonstrating the harmonic contents of the nonlinear. The measurements to be carried out. So the utility should reserve the right to measure the amount of customer's harmonic current injection at any time at the point of common coupling. So that's why here the point of measurement, as I told you earlier, the PCC will be the common metering point between the customer and the utility. That is, both the customer is capable of accessing it and the utility should reserve the right to measure the harmonic current injection at any time. So these measurements are usually spot checks, and but additional monitoring may be required at some constraints. This mitigation device and method. So the customer should be responsible for design, installation and operation and maintenance of the mitigation device required to meet the utility harmonic limits. So the mitigation device may include current limiting reactors, passive filters, active filters or any devices that minimize the flow of harmonic currents onto the utility's distribution system. So the customer should submit the mitigation device maintenance records to the utility upon request, and the installation and mitigation and the testing of the mitigation equipment should be subject to the approval of the utility. The mitigation devices may be capable of handling the IEEE 519 permitted background voltage distortion that can exist on the utility's distribution system. And the solutions are categorized under two categories. The first will be the preventive measures. So here it will be the strict adherence to IEEE 519, phase cancellation, encouragement of low distorting loads and computer simulation. So how we are going to make it? So before designing a system itself, we have to plan the system accordingly so that the harmonics injected by the load into the system are within the limits specified by IEEE 519 recommendations. And further, if any harmonics are present, the system should be designed in such a way that the harmonic cancellation may occur due to the phase shift among the voltages and currents, and the encouragement of low distorting loads, and computer simulation. So computer simulation majorly aids to evaluate the harmonic performance of the system before commissioning of the load equipment. And the remedial measures. So the remedial measures are circuit detuning, are providing a passive filter or active filter. So here the passive filters as the notch filtering, harmonic pairs, third harmonic filter should be avoided because this may cause system resonance, and the higher harmonic order and fewer kVA are needed for a filter. And also the third harmonic filter, since the frequency is very less, the values of the filter, inductor and capacitor required may be quite high, and hence the power rating, size, cost and other factors. On the other hand, we have active filter, which has the capability to operate in the time domain and the current limiting capability and multi-point voltage monitoring. Thank you.